Okay, hello class. This is the first of our virtual GG lectures while I'm in India, and this is our last topic in chapter 7 about sediment movement, and what we're going to focus on is bank erosion and why it's important, the processes that cause it, and of course how variable of a process it is and the complexity. So some examples of bank erosion causing structural damage, and then some of the efforts that we put into trying to protect from bank erosion. We spend on average more than $1 billion a year for bank protection, and bank erosion is also a significant source of sediment supply that our rivers carry. So about 50%, or can be more than 50%, of the sediment carried by rivers comes from the banks. Great example of spending a lot of money on bank erosion and also then maybe it not working and having to take it out. This is along the Rio Grande, north of Albuquerque, downstream from Cochiti Dam. And what they did here, so the Rio Grande used to be a wide, braided, very mobile, very dynamic river that eroded its banks quite a bit. And so in order to try to control it, back in the 30s, they installed these big metal structures. They're called jetty jacks, and they are, about 6 feet tall, and they look like, the kids' little jacks you used to play where you throw jacks and then pick them up with a bouncy ball. And what they would do is they cable these metal things together and they line them up on the sides of the banks, and the idea is that when the river floods and the water comes up and it flows over bank, it flows through the jetty jacks and it loses energy and deposits sediment, and eventually the jetty jacks end up buried. On the Rio Grande, in this part of the Rio Grande, it didn't work out so well because they built a dam which cut off the sediment supply, so the river incised, it degraded. The river is pretty much detached from the floodplain now. And so the jetty jacks are sort of left up on the floodplain high and dry. You don't get overbank floods. They didn't get buried in sediment, but the river is still eroding the banks, and now the jetty jacks in some places have tumbled into the river, where they become a pretty bad boating hazard, and we are now spending millions removing them. So there's some more pictures of them in the river, and you can imagine you don't want to run into one if you're floating. Right. Another example of bank protection is one we're going to visit on our field trip to the Colorado River. So here is Colorado River flowing through Grand Junction. This is the tail race from the Redlands Canal. This bank line right here, you can see there are these little bumps. Oh, notice on this map, south is up. So this map, we're actually like facing the Redlands, right? So the mall is over here. So you can see on the outer bank of this meander, there are all those little bumps. And those bumps are piles of rocks that they have installed to try to keep the river from moving. The blue outline here is the Colorado River from the 1973 USGS topo map. And the background image is the 2001. It's a color infrared image, so vegetation is red. This here is the landslide house. There's that house that's sliding into the river. So here is Redlands Parkway. So the mall is over here. And, if you look at this scale, you can see that the river has actually migrated from 1973 to 2001 about 200 meters. So major bank erosion. You can see how close the bank is to Redlands Parkway. And so they have implemented these bank protection measures to try to protect the parkway. This is a sidewalk that the river eroded underneath. That was in 2002 after the high flows. Actually 2002 was a low flow year, but then in 2005 when it flooded again, those washed out. That sidewalk washed out. These are the rock veins that you could actually see in that map, the little bumps. And in between those, they have cabled together telephone poles that they've lined the bank with, and it has produced a scalloped bank line. So between the rock veins, it's eroded out. So this is at about 3,200 CFS. So the average kind of winter flow. And then here we are at 38,000 in 2008. We're going to go out here on one of our field trips. So, I think that staff gauge washed out in 2011. So I think that's gone. But you can see this platform, that blue platform, will actually go out on that blue platform. So remember that. You can see the water is at it. In 2011, that was actually underwater. There's the staff gauge giving us the height of the river on that day, and all those cabled together telephone poles. Of course, they're wood, so they float when it floods, and not really doing a very good job eroding the banks. But the idea is they just need to provide a little bit of protection between the rock veins. So, and they did lose that whole sidewalk that was being eroded in the 2002 photo. Is actually all, it was over here, and it gets washed away in this flood. So some more images. This is the parking lot at the Redlands boat ramp. All right, and some more views of those bank protection measures not exactly doing the job they were intended to do. All right, so one of the other challenges with protecting banks and figuring out bank erosion is that it's a complex process. And there are two factors that can really confound our ability to estimate how much banks are going to erode, or, to kind of have an idea of what's going to happen, or to measure, predict bank erosion rates. One is that bank materials can be cohesive, of course, and usually we have some fine material in banks because they're floodplain deposits. That can be cohesive, and you can end up with vertical banks that don't fail from sediment just being plucked away. And we'll look at the different ways they can fail. The other thing that can happen is that the vegetations can actually, their root wads can stabilize or destabilize. So what can happen is large vegetation can actually be really heavy and end up destabilizing. We'll look at some examples of that. But then we also can have a situation like this tamarisk that is actually stabilizing this chunk of soil, and so you end up with a little scallop bank line. This is down on the Rio Puerco, but I've seen this exact same thing happen on the Rio Grande. The other thing with roots is they actually promote drainage of banks, which is good. So, the roots can add strength, and they can promote drainage, so they can actually help stabilize banks. Large veg can fail altogether in a big mass failure, so that can be challenging. Another example, so this is just cohesive banks on the Rio Grande, down on the site where I did my dissertation. That's actually my PhD advisor there. And some examples again of, large vegetation nearly failing, and the roots as they stabilize the banks. All right. Oh, so just to give you an idea of doing the surveys, some of the surveys that we did down on the Rio Grande, which we'll look at data of them from those surveys later, this is how we actually got depth. So we would go across the cross-section using a stadia rod. And the banks down here, in some places, there is quite a bit of tamarisk. There is some here, but not a lot. But this is also where we saw that the scalloping of the banks. All right, so the processes that lead to bank erosion. The first thing that happens is that the banks can get pre-weakened because of the flows wetting and drying. So you get repeated cycles of wetting and drying, and it weakens the bank material and gets them ready so that they can be more easily eroded. The second process is just direct entrainment of individual particles. So this is what we've been talking about that we estimate, right, with Hjulstrom's diagram or with the Shields equation, where you get enough energy in the flow, enough shear stress, that you can actually start mobilizing the particles. And if you start mobilizing the particles on your bank line, then you're causing bank erosion, right? So just direct entrainment, or it's also referred to as hydraulic action. And then the third process is mass failure. So this is when big chunks of the bank actually just collapse and fail. So we'll look at the different processes. So direct entrainment, this is what we usually see for non-cohesive banks. So you can tell this bank line is non-cohesive because it's not vertical, right? So it's sloping. not quite vertical. And this will happen more for the sand size and gravel size particles. So the non-cohesive size particles, little larger ones. And this will occur when the velocity and the shear stress are high enough in the lower region of the banks, and they start plucking away at that material. And then eventually you end up with some failure. So whether or not this happens is dependent upon the velocity conditions in the channel and that velocity gradient. Remember, we looked at how velocity gradient is related to shear stress, and the steeper the velocity gradient, the higher the shear stress. We tend to get higher erosion at outer banks of meanders because we have that steep velocity gradient, high shear stress. So, and that shear stress then entrains the material and destabilizes the bank. Then we can end up with mass failure. So what this is just coherent blocks of material actually failing, and they can slide or they can topple. Oops, go back. You can end up with rotational failure. So similar to, we talked about landslides when we're talking about hill slope processes, it's still mass wasting, same thing. If you have fractures that occur from cycles of wetting and drying, that can, like I said, that can pre-weaken, sort of prepare the material for failure. So having some kind of failure plane, of course, makes it easier for this to happen. And the other thing that's key is erosion at the toe of the slope. That's also destabilizing. So erosion at the toe increases that bank angle and makes it easier for mass failure to occur. This can happen with cohesive layers. Also, the failures are more common or happen more easily if you've got a cohesive layer over a non-cohesive layer. So that hydraulic action happens at the toe. The entrainment from the flow happens at the toe, and then you get the mass failure of the chunk of cohesive material above it. Often this happens after the banks have been saturated with moisture. So this can happen when you have hydropower releases. So you ramp up the flow for hydropower, the banks get wet, you drop the flow, you leave saturated banks behind with positive pore pressures, all that extra weight from the water, and then you end up with mass failure. Water also acts as sort of a lubricant, so it allows those grain-to-grain contacts they're not as strong, and then it can also reduce cohesion. And like I said, you can end up with high pore pressure. And some examples. So here's a chunk that toppled, right? So that's toppling. This whole chunk here used to be vertical up here, right? Another big chunk. So here's another mass failure. And more. And so again, sometimes the vegetation contributes to this because it holds it all together as a mat and it all fails together. So more examples of mass failure all along this outer bank of this meander here. And this is the outer bank of a meander. It actually doesn't have mass failure on there, but you have undercutting. So on this one, you can actually see that you're getting erosion at the toe that's leaving behind this big chunk of cohesive material unsupported. And so that's sort of setting the stage for potential mass failure. So that helps sort of see the action that occurs that results in the mass failure. So here, for example, where do we start? Down here. So we have coarse, non-cohesive lower bank and fine-grained cohesive upper bank. So let me go back up one. So down here, you can see the larger cobbles. And so you erode away underneath and you leave this chunk unsupported, and then eventually it can fall off. This example here is showing how water movement through the material can actually help lead to failure. So where you've got water flow moving through a sandy pervious layer and then some erosion that leaves this unsupported, and then you end up with toppling. And more examples of non-cohesive material underneath cohesive material, leaving it unsupported. This is a plate from your book, actually. And again, undercutting and leaving cohesive material unsupported. And you can see how big chunks of this material have failed. So the cohesive material fails in chunks. Oh, right. So bank erosion can be highly variable. Rates of bank erosion are very variable, but we often measure them as an average. So for example, we might go out and survey a channel one summer and then not survey it maybe for 3 or 4 summers or even 10 years, or there's a longer period of time. And then what we usually do is, so we measure, let's say it moved 2 feet, and it moved 2 feet in 2 years. So we say that was an average rate of 1 foot per year. But the reality is all 2 feet might have happened in one flood. So the reality is bank erosion is really episodic in response to flow events, but our measurements are often averaging over a longer period of time, which might result in an average rate that's masking the real variability in the system. So that's one of the problems with the way that we measure and the way that we tend to average. There has been some work trying to correlate other stream variables with bank erosion rates. And one of the best correlations is with stream power. So stream power, using multiple regressions, was shown to describe 48% of the variability in erosion rates, which it makes sense. Multiple peak storms can be more effective. So because if you have wetting and drying, you pre-weaken the banks, and they're more susceptible to erosion. And so if you're in a climate where you get winter storms one after another, you may actually have a seasonal bias with the bank erosion, where you have more in one season or another. So stream power tends to peak in the middle reaches of a stream, where your discharge has increased but your slope hasn't decreased too much. And that's where we tend to see highest rates, actual highest individual rates. So if we're averaging over time, I should probably make a graph or something with this. So right, you may have in the middle reaches, you might have an individual event that is really big. But averaged over time, the average rate would probably be smaller in the middle reaches than in headwaters reaches. So if we go up into the headwaters, the average is probably going to be higher, but you may have incidents of higher erosion in the middle reaches. And local site characteristics are hugely important. There is high degree of spatial variability in bank erosion in even a single reach, just depending on what's going on with the underlying geology, whether you've got tributaries coming in. There can be so many different factors. Vegetation and bank material, of course, are really important. There are other factors that contribute to bank erosion. Grazing and trampling, so grazing in the area, and the cattle and sheep have been shown to contribute to bank erosion. Frost, freeze-thaw action, invasive vegetation and removal of invasive vegetation both affect bank erosion. And here is a nice little summary table from the great Knighton book of different factors that affect bank erosion. So you can see the flow properties, magnitude, frequency, variability of discharge, of course, velocity and shear stress, and turbulence. So, of course, all of these factors related to flow. The size of the bed material particles, the gradation. So do you have a more well-sorted sample or a more well-graded sample? How cohesive it is, and is it stratified? The climate, what your rainfall is like. Do you have like intense gully washers, really high-intensity, short-duration storms, freeze-thaw action, subsurface processes, piping, seepage, pore water pressures, the channel geometry, the radius of curvature of the bend. So a tighter bend is a shorter radius of curvature. What's going on with animal burrows, grazing, trampling, and then, of course, all the urban human factors as well. Oh, and then of course we build bank protection structures, what keeps the river from moving around. So some examples of bank erosion where animals come down to the water, and another one in Costa Rica. And, oh, I have more pictures from the Yampa that we'll look at. Okay, so how do we measure bank erosion? We can actually put pins in, survey cross sections, or look at aerial photos, and we'll look at a couple examples. So these are erosion pins. So there's actually like a stake driven into the bank, and you can measure how it erodes. You can see this debris cone from weathering. Sedimentologists refer to this as subaerial processes. It's basically happening at the surface, meaning in the air. So submarine is within the ocean, below the ocean surface. Subaerial means below the air surface, like high. It means it's in the atmosphere. So it's a surface process, a superficial process. So weathering and erosion is a subaerial process. So we've got subaerial weathering erosion creating this debris cone, and we have these erosion pins here, which we can measure then how much the bank has retreated. And another bit, oh, you can actually see there's been some desiccation around the pin, so that sort of chunk that's fallen out. So that's another thing that can happen with wetting and drying. As it dries, it desiccates and kind of slakes off. We can survey cross sections. So this is on the Rio Grande, downstream from Cochiti Dam, which was constructed in 1973. So the little dashed line was in 1970. And then the darkest line is 1998. So you can see that bank retreated. It's about, 10 feet or so of bank erosion. And this is in the outer bank of a meander. This whole channel shifted and has developed an island. And one of the things that happened down there is a lot of these little islands became vegetated. Once the dam was built, cut off the flood flows, vegetation encroached, and then there aren't floods to wash the vegetation out, so you end up with really stable islands, and the river is sort of locked into a more narrow planform rather than being braided and carrying a lot of sediment around. So this is, let's look at this is about 120. These are meters, not feet. So that was 10 meters of erosion, and this is 120 and about 90, so 30 meters of channel movement there. And similarly, using aerial photos, this is again on the Rio Grande, downstream from Cochiti Dam. The yellow is the active channel in 1935, and the orange is the active channel in 1949. So we can measure, and in this case what we did is we measured at each of these cross sections how much the bank line moved from one year to the next. Now all of this movement, that's like 300 meters of movement on cross section 68. We don't know when it happened, right? We have the air photo in 35, the photo in 49. So we've got 14 years. So we would say 300 meters in 14 years, come up with an average rate, but that's not really telling us what happened when that erosion really occurred. So it may have occurred when there was one big flood, which I think there was in the early 40s. So, all right, so to give you some ideas of magnitude of erosion rates, which actually kind of puts that 300 meters of erosion in perspective. Again, we usually report in average rates in meters per year, feet per year. This tells you how many years that average was done over, but you can see some of the highest rates are in the 4 to 5 meters per year. 4 to 4.5. Oh, except for this river down here in Poland. So 8 to 10 meters per year. So, these lower kind of rates are not that uncommon, and more mobile rivers can have higher rates. So a lot of variability actually in the rates of erosion. Okay, another example, looking at the Yampa River at the Sevens Ranch. So this is up in northwest Colorado. To give you an idea of where this is. So this is Moffat County up here in northwest Colorado. The Little Snake River flows in from Wyoming, carrying a bunch of sediment. The Yampa draining, so this is Craig, where the big coal-fired power plant is, so steamboats much further upstream. We're looking at the Sevens Reach right here, which is just upstream from Cross Mountain Canyon. Lily Park right in here is where the put-in is for the Yampa Canyon. So Dinosaur National Monument's like right here. So we're upstream from that in a really highly grazed area. So the Sevens Ranch is actively grazed. So this is looking upstream on one of the cobble bars in the river. The Yampa there is still a pretty natural river from the perspective of its flow regime. There's no major storage reservoir above this area, so the river's flow regime is pretty natural. And to give you an idea of the grain size, so not that dissimilar to what we saw in our cobble bar on the Colorado River, right? So some fines, deposition of fines, and then also some, we get into, you can see here some gravel and then into cobble size. This was a cross-section endpoint pin that was probably 10 meters away from the edge of the river about 2 years before this photo was taken. So this was a cross-section that Colorado Parks and Wildlife, we were surveying, and we'd come back out to find them to get ready to do another survey, and discovered that the bank had moved so much that the pin was now right on the edge of the river where it previously had not been. Just upstream from that, there's a fence, and you can see now this fence is right at the edge of the river. When we came back again after the 2000, I think it was actually in 2005, when we had a really pretty high flow, and this fence was actually in the river, and actually on the day we were there, there was a dead calf that had gotten tangled in the fence and drowned. It was kind of awful. But so we know that this bank line has actually continued to move. So you can see vertical bank line over here. So we know that when it's that vertical, we know we've got at least some cohesion going on. When the cohesive material is really dry, it can actually be really tough and doesn't erode very easily. All of this is from trampling from the cattle, and I'll show you a picture of where they are, because they come down to the river to get water. And there's a notebook there for scale. And here we go. So this is one of the spots where they come down for water. But all of this, let me back up, this trampling is from cattle, and this land is very intensely grazed. So we did some measuring with aerial photos, and over here we have the 98 aerial photo, and the lines are the 1953 bank line. And so you can see there's about 20 meters of movement here, 20 meters here, and about 20 meters there. The northwest side of the river over here is up against a bluff, and it does not move very easily. On this section of the river, again, we're going from 53 to 98, and this is about 30 meters of movement, but that is clearly on the outer bank of a meander. So you can see there's some places where there's some evidence it may be actually widening. In this case, it's just natural meander migration, probably. But we didn't see the point bar move quite as much. So, all right, and every time we went out there, the cows thought we were going to feed them, because of course the ranch hands that feed them drive out in a big truck, and so we drive out in our big truck, and the cows would come up and surround the truck, and it was a little disturbing. So, all right, so there we have it. Thank you, Erosion. If you have questions, post them in the discussion section for this section in D2L, and refer to your textbook in Chapter 7, like it's around page 96, 97. So, all right, I'll see you again soon for another video.